I don't know if it'll just be you and me again, but that'll be okay. All right, so let's carry on with where we left off on Tuesday. And okay, so where we left off on Tuesday was that we had the DPF systems, and there was the big question of all the soot comes down out of the exhaust on those things, and what's it do? Okay, it's a wall flow filter. It means that you understand what that the tubes is going through the tubes and going to the other side, and that's how it works. In fact, just for your edification, the 6 liter and the 6.4 diesels, their air filters were the same design. They used a paper cartridge, but it was the same kind of idea, the same wall flow kind of design of gigantic, big gigantic thing, and they could hold over 2 pounds of dirt and have zero restriction because there was so much surface area of filtering. It's a design that they picked up from the Abrams tank in the deserts. That's what they use to filter the air out of filter the air coming in the engine and those. And it's just a super efficient air filter that cleans really well and holds a lot of dirt. And you can just take them out. You can shake them out and dump all the dirt out of them and keep going. They're really, really good. But it's the same thought process anyway. But they do plug up, and they plug up in a diesel pretty quick, because if you look at a diesel that doesn't have a filter on it and you watch them accelerate, you'll see black smoke coming out the tailpipe. Well, that's all soot, and that's what we're trying to capture with this filter. So they plug up pretty quickly. And so then the question is, well, how long will they go, and how what do we do about it? How do we clean them? Okay, well, the distance of how they're going to go is really going to depend on a lot of things. It's going to depend on the quality of fuel being used, the load being carried, the temperature of the engine, all kinds of stuff's going to determine how much soot is actually coming out of there, and if that soot's going to plug up or if it's going to burn off naturally. So the answer to that question is, who knows? I've seen trucks that there's one of the things that all the world wants to do is put on a delete kit where they'll take the exhaust off it and then put a program in there so it ignores all the pressure and temperature sensors and just gets rid of the exhaust system completely in there and just blows all that soot out the back. Well, in California, to get it smogged, you have to have all that in there. We actually have to go look and make sure that it's all in there. Well, what people will do is they'll quickly put it all back underneath there and not change the program. So if you put all that exhaust in there and don't change the program to remember that it's got to clean itself, within 100 miles, that thing will be plugged up solid and can't be cleaned. Because we'll explain how we clean it here in a minute, but to be able to clean it, you have to have hot air go through it. But if we've clogged it up so far that we can't get hot air to go through it and bake and you cook off all that soot, then you're done and you have to replace it. So it can get kind of expensive messing with that stuff. So the question then is, how do we clean them? Well, we use a process called regeneration. They call it, for short, we call it REGEN. They'll also, if you see it on the instrument cluster, it won't say regenerating or anything like that. It'll say cleaning exhaust or exhaust cleaning or that kind of thing. But the idea of it is all the same. We're going to clean the exhaust. So there's several methods in which we do that. We're going to do it passively, actively, or we can do it manually. We can force it to happen. So passive generation is just like we say, it's a passive thing, just like passive restraint systems is the same kind of an idea. An airbag is a passive restraint system. In other words, we don't have to do anything to it. It just protects us, as opposed to a seatbelt is an active restraint. We have to put the seatbelt on, and so we're doing something to make that restraint system work. An airbag is passive. The only thing that makes it work is, smacking a brick wall or hitting a car that you're not supposed to hit. Okay. And it just happens and does it all by itself. Same way with passive regeneration. It does it all by itself without any inputs from the driver, no inputs from the computer. It just, what happens is it uses exhaust heat naturally produced in the exhaust in certain situations, and that heat just naturally starts to cook itself off. So let me back up so that we kind of understand what has to happen here. That soot that's in the black soot that's in the exhaust is organic. Okay. And being organic means that it can be burnt. If it's inorganic, it won't burn, like let's say a rock or something like that. You can't burn them. They're just going to be there. When we cook, like when this comes down to ash no longer has any organics left in it, and it just is in there. An example of this is, and you'll see it, I think we talked about the fireplace and that kind of thing the other day, inside of a fireplace. A fire, especially when it first starts, I have a pizza oven outside that when we first start the wood fire in there, it's all black and really sooty and really, it's just gross. And then, but as it heats up, and it all depends on the temperature of the product that it's trying to burn off. But as it heats up, it starts to burn that off, and it'll be crystal clean. I mean, my pizza oven gets so hot that it's super clean, and it just cleans itself off. In the same way, inside of a fireplace, the fireplace will be all sooty and gross, but then as it gets hot and you really heat that thing up, it burns all that soot off. It's because it's an organic matter that can be burned off. And that's exactly what we're doing inside this DPF. At a certain temperature, they're saying in the 400, and I think they said 480, I think it's like 483 degrees or something like that. At those temperatures, it starts to burn that organic matter off. So, one of the problems we talked about with the DOC is the cold exhaust that happens inside of a diesel. Well, remember that when that exhaust gases are passing through that DOC, they're going to start making heat, because as we convert the oxygen and the hydrocarbons or the carbon monoxide into CO2 and water, the byproduct of that is heat. Any of that heat then comes through and gets into the DPF, and it starts to cook off that soot in the DPF. And that's what it just does it passively. It just does it, we're driving down the road under a heavy load. We may be making ash or soot, but at the same time, we're creating a great deal of heat. So we're burning off that soot in the DOC as well, but we're also creating enough heat to cook it off in the DPF. And so it just happens. It just naturally happens. And I think I got a pretty good slide here. This is, you have your nitrogen monoxide and oxygen coming through here, and it gets, and it's going to blend with your hydrocarbons and CO2 and create things. But I think in this slide here, what we're really talking about is the oxidation process that's taking place between the nitrogen and the oxygen, and it ends up producing the nitrogen dioxide, which is, remember, it's a bad gas. However, the heat that's taking place in that is good. It creates a lot of heat when it makes that chemical reaction. Okay, so then as the NO2 it combines with the carbon soot in there, and it creates more heat, and it all just kind of works out and cooks off a bunch of that soot, and we end up with CO2 and nitrogen. So, or a nitrogen byproduct, or an N2 is just a different nitrogen that's okay. So all of that's saying, and the chemistry of it is stupid. It's not that important to us, other than the fact that it's heating up and it's cooking the DPF off passively. It just happens because we're driving down the road. Usually it's not going to happen at low speeds. You're going to be, over 30 miles an hour and with a fairly decent load, and all that heat that's taking place just cleans the exhaust naturally. That makes sense? Okay. So our next one then is going to be an active regeneration. Okay, so um, what happens with an active regeneration? Let me see, that phone's ringing. Let it ring. The an active regeneration is when the exhaust becomes loaded. It's going to become loaded beyond what it's allowed to be, and it's going to start becoming an exhaust restriction. So the computer, we'll talk about how it measures all that, but the computer's going to say, hey, the exhaust is getting too plugged up, so we're going to have to do something about it. So it's going to command strategies to start cleaning the exhaust, and we're going to use heat generated by what we're going to call hydrocarbon dosing to make this happen. And that heat is then going to burn the soot off in the DPF. So what is hydrocarbon dosing? Well, hydrocarbon dosing is when we're going to actually add fuel to the exhaust in front of the DOC, okay, in front of the catalytic converter, and that's going to be let me back up a little bit when we talk about those catalytic converters. In a gas engine, if we have a misfire, like a spark isn't firing, and we're putting raw gas down an exhaust in a gas engine, it heats up a catalytic converter so fast and overheats it and it actually melt them because the heat that's generated from the from the hydrocarbons burning in the exhaust. So when we go back to this hydrocarbon dosing, we're going to put small amounts of vaporized diesel fuel in the exhaust. That vaporized diesel fuel is going to get into that DOC, which is the catalyst. And that catalyst is going to, remember, we have an oxygen rich situation down there. So it's going to start oxidizing that fuel, and it just cooks up, and it creates heat, lots of heat real fast. Okay. And I actually have a recording we'll watch in a little while of that taking place. But that hydrocarbon dosing heats up, and we have what we call a flameless combustion taking place inside that DOC. And that just creates a superheated gas, in the, usually 900 to 1200 degree range coming out of that catalytic converter. And that goes into the DPF, and that superheated gas cooks all that soot out of there. Okay. And it is a process called active regeneration, where it is for a given period of time, it's going to do that. So you'll be driving down the road, the customer won't even know that it's happening outside of, depending on the model year and the vehicle, it might flash up a thing on the, you might get a couple messages. One of them might say, hey, it's getting kind of plugged up and you haven't got it cleaned in a while. You get a message that comes up and says, drive to clean exhaust. May or may not happen. But you'll be driving down the road and it might pop up a message that says, cleaning exhaust. It might come up for a second and go away. Some models will come up and it'll stay there the whole time that it's happening. It really depends on the vehicle, the year, the level of cluster that's in it, all kinds of stuff. And it may not give you any idea it is, but it'll go into a regeneration. And when it's going into that active regeneration, it's going to, well, let's talk about the 6.7. Well, yeah, it's going to put that fuel into the exhaust. And when it's doing that, it's going to affect the vehicle is going to run a little different. It's going to sound a little different. It's going to smell different. You can really kind of smell it in the exhaust. But as long as all the conditions are met, that'll stay in that state. But if the customer comes to a stop, it could stay in the regeneration. But if he puts it in park, boom, it'll take it out. If the truck didn't have enough fuel in it, or there's a lot of different scenarios that'll stop it from happening. But generally what it's going to try to do is it's going to start it, and it's going to try to get it all the way through and complete it. Now, if it doesn't complete it, okay, that can be okay, because it could actually clean it and be perfectly clean, yet had not completed a process. But when it's done, or it got interrupted, or you stopped the vehicle or something like that, and it didn't satisfy the fact that it was completed, Well, then the next time you get in it, it may not need it right then, but it'll go, and the next time it needs it, it'll go through. And if you say it goes through and it says, yeah, you didn't get it clean or you got it clean all the way, and then you turn the car off, but it didn't complete it, then it goes and does it again. And it doesn't care that you didn't complete it until you get to the magic mark of 761 miles. Pretty sure that's the right number. Okay. And I don't know who came up with this number. It's probably legislated or something. But if the vehicle doesn't complete one in a certain amount of miles, then every time you get in the car, it's going to go straight into a regen when you start driving it until you get it to complete. And why is that important, you say? Well, if the customer just, and this is it's not so much a problem on the 6.7s, but it was because on the 6.4, because that was kind of a new technology and just was kind of a lummox. But you get a customer, and this was real typical. Customer buys a truck, and she wants to, it's some gal, she wants a 4-wheel drive truck, and she's going to drive, and all she's doing every day is taking her kids 3 blocks to school, dropping them off, going home, parking it. Gets up the next day, drives there, boom, back and forth. That's all she does. I promise you, this thing will never go into a regen or ever finish a regen in that amount of time if it ever went in. So now this customer, she's driving it back and forth, and it needs a regen. So it goes in it, and it never finishes. She goes 700 miles or 761 miles, and now every time she gets in it, it's in a regen every single time. So the car's always in a regen. Well, this hydrocarbon dosing, and we'll talk a little bit more about it in a second, but it's putting fuel in the exhaust to make this happen. Well, that just ruins your fuel economy. Okay. So the customer will be like, either the message will come up and say cleaning exhaust, or they'll come in and say, my fuel economy just pits, or it's always in a regen. What's going on? Well, what we need to do is kind of school the customer on it. It's like, hey, you know what? You need to pack those kids up some afternoon, take them for a ride to the mountains every once in a while, and just get this thing cleaned out. It just is what it is because of the design of the vehicle. The 6.7s are a lot less susceptible to that, but the 6.4 was really susceptible to that. But let's talk a little bit more about this hydrocarbon dosing. So there's a couple ways that we do it. And let's start with, I've already talked about the trucks, but I'll go into that deeper in a second. But the Transit, the 3.2 Transit in the, the big space shuttle looking vans with our little 3.2 Puma motor, they use what we call a fuel vaporizer to do it. And what they do is this unit is screwed into the exhaust just before the DOC. And you can't see it, unfortunately, but in this tube down here, there's just a little hole. And what happens is this tube here is connected to just a little fuel line that goes down to this little itty bitty little pump. And it just dribbles fuel. I mean, it doesn't pump. It's like, what is this thing doing? It just dribbles fuel. Okay. And it's just a little dribble of fuel that comes in here when it's commanded. And it just dribbles fuel in here, and there's a glow plug in here that gets to like 1300 degrees, and it glows red. And so they put this fuel in there, and as the fuel dribbles in here, it vaporizes the fuel, and that fuel dosing just sprays down in front of the catalytic converter, and that fuel, that vaporized fuel, is what doses that DOC to make the heat we need, and it works really effectively. We'll see it's a little slower process than the post-combustion injection events, but we'll see temperatures in the 1200 degree range in the going into the DPF. It works really well. And with this process, we don't have the risk of putting fuel in the oil like we do with the others. And I'll explain what that means here in a second. So that's how we do it in the Transit. In the 3-liter Ranger or F-150 motor, the 6.7 and the 5.4 or 6.4, we do what we call a post-combustion combustion injection events. And what that means, remember with our common rail fuel system, remember we had the ability to do pilot injection with a little injection in the beginning, and then we could do a big injection event, and then we could do post events. Remember we had some post events that we would have in there that would cause as the thing was cooling down, we could put some fuel in there and burn off soot in the cylinder. Well, what we're going to do is we're going to fire that injector when it's on its exhaust stroke, when it's pushing the exhaust out. We can give it a shot of fuel, and we can push that out of the cylinder, and we're going to put our diesel fuel in the exhaust there. It's called a post combustion injection event. Okay, so on the 6.4, we did that with all 8 injectors, and it worked fine for what we wanted it to do. However, when you're putting raw fuel in the cylinder, and it's not really burning or doing anything with it, fuel would get past the rings and get into the oil. So that's a problem for 2 reasons. One, the 6.4 would, especially a vehicle that was loaded a lot and they didn't change their oil when they should, well, you would actually grow oil. The 6.4 will actually make oil in its lifetime. So between oil changes, if you think most cars will use a little bit of oil, it'll drop. The 6.4 will grow oil. And if you don't change your oil regularly, you can fill up to a point where it'll actually start pulling it through the crankcase ventilation system and run away on that diesel oil. Very common, happens all the time. Okay, bad things happen. Okay, so that's one of the first things you're going to do with a 6.4 when it comes in and they got a complaint of anything. You can pull the dipstick out and say, how much oil's in this thing? Are you changing your oil? Because there's other reasons fuel can get in the oil, but that's a biggie. Okay, so the second real problem that we're going to have with doing that, especially on the 6.4, was if we're going to use biodiesel, which these things were capable of using. I think the 6.4 could use B5, which is 5% bio, and the 6.7 can use B20. Well, the biodiesels, and they can actually, you can actually run them on pure biodiesel, and you'll get some fleets that'll try to do that. Well, the biodiesel, when it goes down and gets past the rings and gets into the oil, well, it doesn't evaporate the same way as regular fuel does. And so it creates problems. And what I actually had one in a 6.7 come in, and the oil had the consistency of, I want to say Jello, but it was more like a Cool Whip. Like it was black Cool Whip, and what happened, you can't pump Cool Whip. so this engine starved itself for oil, and it just melted down because it couldn't get any oil, because it was all, and that's a result of the biodiesel in the oil. So you end up, if you're going, and one of the reasons that modern diesel engines have such gigantic oil capacities, we're holding 13 and 15 quarts of oil. The reason we're doing that is because in order to go 5,000 miles on your oil change, they needed to, and use biodiesels, they needed to have enough oil in there that it could handle that kind of thing. But if you overdo it or don't change your oil, then you end up with a big problem. So at the end of the day, it's just, we don't have a ton of problems like that, but that's kind of one of the things that happens. Now, in the 6.7 and the 3 liter, however, we're going to only use the left bank. We're not going to do all 8 cylinders. We're only going to do the left bank, and we're going to just hydrocarbon dose it that way. We're just going to send some fuel out that way. I don't know why they chose the left bank, not the right bank. I don't know. I'm not the engineer, but that's what they're doing. And so that's how they're getting the hydrocarbons in there to make that happen. And Let's see, do I need to talk about anything else with active regeneration? And when we say it's active, it has really nothing to do with the driver, other than it may tell you, the driver, it may say, hey, drive to clean exhaust. And so, you know, it's incumbent upon the driver to then drive the vehicle. So I don't think, let me make sure I'm not missing anything. The magic temperature number is 482 degrees, however they came up with that. So one of the things when we talk about the temperatures that this thing needs to do that, the DOC, when a properly working DOC, when we start dosing this thing, we want to see pretty quickly at least a 200 degree temperature split between the temperature of the air coming into it and the temperature of the air coming out of it. And then that air coming out of it's going into the DPF. And this is an interesting thing, what happens if we don't. The really common in the 6.4 engine, if that catalytic converter becomes poisoned, and when we say poisoned, it doesn't no longer work, whether it got coated with something that doesn't work or anything like that. So the catalytic converter now is cold, or it takes a long time to heat up. Well, we start dosing that thing, and think about this fuel now is going into this converter and it's smoldering. It's not combusting and burning and getting hot. It's smoldering. And what diesel fuel, when it smolders in exhaust, it turns white, like real white, and it turns into this white, smelly exhaust. You've probably seen a big giant diesel truck running down the road before with white smoke just billowing out of it. That's because it's because it has some kind of a major fuel system error or problem. And we don't, and a black smoke would be like it's trying to burn it, but it didn't burn it all. White smoke's just raw vaporized fuel running out the tailpipe. Okay. So what happens is the 6.4 in a kind of a cool morning, like we've had some cool mornings lately, guy goes out and he's driving it and it tries to go into a regen, and it starts putting that fuel in the exhaust, and literally these guys will go, maybe a whole block, and it will just billow large plumes of white smoke out and completely block out the intersections, with this white smoke. And then it'll eventually kind of clear up and work and go on. And that's a result of that catalytic converter, or the DOC, not heating up. It's not as efficient as it is. And so the fix for that is to change that out and then it heats up properly. So then the third is, you understand active, all of that, all computer controlled active regeneration. Okay. The third one is they call it forced, or we'll call it a manual regeneration in the Ford world. And you can have situations where like trucks that can't necessarily go get their exhaust clean or drive them around. Maybe a drilling rig, guys drilling wells, and he's using the power takeoff unit on that truck to, with the engine running to drill, to run the drill, to, drill a hole, or a trench line truck, a lot of different, work truck kind of situations where they can't get them out and drive them and clean them out. Okay. So in that situation, the thing will just sit there and plug up, or you gotta, cause you can't go drive it, or you're going to put it through what they call a forced or manual regeneration. And all that is, message will come up here. It says exhaust filter full. It might say, it might give you a percentage, a couple of different, different cluster packages is going to tell you, hey, this thing needs to be plugged and it needs to be cleaned. And when this thing's actually in some of the Fords, they'll say, when it happens, it'll say, do you want to clean it? Okay. And the driver would then in his cluster would say, yes, I want to. And it'll give you a series of commands that you're going to make sure that the vehicle stop, the brakes on. It's got to have at least a quarter tank of fuel, no overheat codes, AC is not on. It'll go through a whole list of things to make sure that it all works out good. And it'll just sit there in a stationary situation and clean the exhaust. It raises the RPM pretty high, turns the fans on fast. and just goes through, and it could take as much as 40 minutes to do it. But it will do it for the driver right there, so that he doesn't have to take it off site or do anything, so he can just kind of get it cleaned up. Now, that would be a forced regen by the driver. Okay. But we also have what we would call in our world is a manual regeneration. And that's where we as a technician might be in a situation where the guy comes in and, he's complaining of some different things or something, and we're forced to put the vehicle through a regeneration. And we can do that through the scan tool, the IDS. And I think the next slide here is actually one that I'm doing on a vehicle, and we can watch all the temperatures, and we can watch the soot cook off it, and we can go through that procedure and make it happen. It's all done. We do it with a scan tool. We kind of command it with a scan tool, but after we command it, it all happens by itself. It's nothing that we have to do other than start the process. And I think this is one right here.
Okay, so we're going to do a manual regeneration in this truck.
Is that working for you? Can you hear it?
But there's a TSB.
Yeah.
So we're going to come in here to toolbox, powertrain, service functions, and then we can pick manual regeneration.
Sorry, my microphone in my computer's not real good when I did this.
Make sure the vehicle's in park. Everything and okay, so this is the numbers that this thing's really at. So in reality, this thing isn't necessarily needing any kind of regeneration, but it's requiring us to do it. Sort of.
So let me back that up for just 1 second, just to give you so you look on the side here, 50 to 99% is partially loaded. Okay. 100 to 120% is fully soot loaded. And then 121 to 199% is overloaded. And then above 200 is considered clogged. You can sometimes get one that's over 200 to unclog, but usually if they're clogged, you're screwed. You can't get enough air through them to cook them. But all the rest of them, we can usually run a regen and get them to clean up. So this one at 55% is not very plugged up at all. However, I was required to do it based on and this inferred soot is grams of soot, and how much, however they figure the grams of soot are that's in there.
So it's going to get 3 mornings. We want to do a static. You can pick to drive down the road, but we're going to do static generation here. And here's just a whole bunch of criteria that it's going to tell you it's going to do. The exhaust can get up to 1200 degrees. Cooling fans are going to run. It's going to be really noisy. All kinds of stuff.
It's really annoying.
Continue. It continues to be ready. And you can see these are our exhaust gas temperature sensors. This thing's just been sitting here idling. They're all pretty even. And we can see our soot, the inferred soot load here. You can see here, if we go here, it'll tell us on the bottom here it is DPF soot concentration. It's inferred. I mean, it's not a real number, but it's factored in. And there's the percentage of load, and that's factored in as well. You can hear the fans starting to kick up on this thing. I'll roll the window up so that we can keep the noise down in here.
But watch your exhaust temperatures in here. I'm going to fast forward here in a second.
Okay, I jumped ahead a little bit so I can kind of warm up. But you can watch the EGT12 start to increase in temperature. Because remember, now we're giving some post-injection events, post-combustion events. So now we're putting fuel in the exhaust. We're calling that hydrocarbon dosing. And that hydrocarbon dosing is going to heat up inside the oxidation catalyst. And look at it. I mean, it's probably 50 degrees out here this morning, really cold. And look at how quickly that catalyst heated up on this thing. Okay, and we should be able to start watching as that number starts to burn off, and we should be able to start seeing the load and the soot load start to diminish. We're at 1100 degrees. We want to see a minimum. We want to see a minimum of 200 degrees above EGT 11. So we want to see a split coming across that oxidation catalyst of about 200 degrees, but it'll get bigger than that. It should get up to around 1200 degrees.
If you'll notice that
This could run for as much as 2100 seconds, which is about 40 minutes.
that load percent, if you watch it, it's actually gone up. It's gone up as it's run, and that's because as it's loading, it's starting to see, it calculates it based on the pressures going through it, and we'll show you some sensors in a little bit.
Fast forward ahead so that you don't have to sit here and watch forever. And you can see the number, and it climbed to as much as 59%, which will happen because remember it's an inferred number, and so it's going to pick up. It's calculating that number based on airflow coming across the mass airflow sensor, how fast the engine's going. It knows exactly how much air is coming through this motor based on RPM, because it knows how much volumetric efficiency this engine has. So it knows, as it's flowing exhaust back there, it knows exactly how much should be going through there, and it knows its percentage of restriction. So you can see that number just dropping off. I mean, just sitting here yapping at you, it has come from 55 down to 51%. And that'll just continue to fall. And you can see we're almost a 300 degree split between EGT 11. Here, this is your exhaust. This is raw temperature coming out of the engine, 900 degrees. And then this is the temperature coming out of this is actually coming out of the turbocharger. And then it goes through the oxidation catalyst. And so that hydrogen dosing, hydrocarbon dosing that we're putting through there is cooking that cat, and we got almost a 300 degree split there. And then at the back half of the DPF, we're cooling down by about 200 degrees. And then this is the actual temperature after the SCR. So we are at 1100 degrees there. And these would be pretty typical numbers. So we dropped down to 46%. So I'm going to go ahead and fast forward you to a little bit cleaner so you don't sit here and watch this. Okay, we're dropping back in here. We're down to 26%, 2.2. I don't even know if that's a percent. That's not even a percent. It's just a number for soot.
It's grams.
Soot concentration. Grams. 2 grams of soot.
Remember that 500 grams is a pound. So it's not really very much soot by weight.
Go ahead and fast forward here. Fast forward here. Look at us now. We're down to 0.8 grams of soot and 9%. And we've been going now for what? 10, 20, 25 minutes. It does take some time. Driving down the road, they'll usually go a little quicker, but it all depends on how much they're loaded and how fast you're going and all of that stuff. So let's pause it for a little bit. Fast forward. Okay, so we've crossed over from the regeneration phase and brought it down to 4% and 0.3 grams of, 0.39, 0.4 grams of soot. and it goes into a cool down phase now for 2 minutes. And it can continue to clear itself more in the cool down phase, but I don't typically see much of that. Anyway, that is a regeneration, and see how instantly, as soon as we brought the temperature or the RPM down from the engine, how the HT11 instantly cooled down 300 plus degrees, and everything else will start to cool down. So there you have a regen.
Kind of cool. That's what's happening inside that exhaust as we see that thing cook off. So what happens at the end when we cook this thing off? We'll ultimately, a lot of that soot just kind of goes away, but there is some of that cooks, some of it cooks to and just turns into gases, CO2 and water, and it just cooks off. But there's a certain level of what we would call ash that happens inside there, and each of those tubes will eventually just collect a certain amount of ash. Okay. Remember that a filter becomes, any kind of an air filter or this kind of filter, the more it becomes plugged, the more efficient it is, which means it's going to let less air flow through. So over time, we'll end up with an ash loaded DPF, and there's nothing you could do with that. I don't know the answer to how long that is. I mean, I've got some 6.7s that have been on the road for over 450,000 miles, and they still have the original exhaust in them. I rarely ever have to replace a DPF because of ash loading. I will have to because of clogged, because they didn't have it. Something went wrong and it didn't regen properly and it clogged up, but that's clogged with soot, not piled with ash. So there's, they do have a lifespan. I don't know what that is. And it really is just going to depend upon the vehicle that's, and everything. So, okay. So so you get all that, how the regen all takes place. We're good to shift gears and get away from that. Okay. Did you know that any of that took place?
Nope.
That's cool. I'm glad I'm able to impart some wisdom to you. Maybe not wisdom, but knowledge. How about that? Okay. So how do we know how these things are plugged up or anything? So we're going to have DPF monitoring, and it's really going to be very simple. We're going to have pressure sensors and temperature sensors that are going to deal with it. Temperature sensors have nothing to do with the pressure loading, but they're going to have everything to do with how everything's operating. But we're going to have pressure sensors. They're either going to be a single, like this one here, just nothing more than a pressure tube going into a pressure port in the DPF ahead of the DPF, so that as the air is coming down, we can know the pressure of the air exhaust going into the exhaust, so that if that if that pressure or DPF becomes restricted, we can see the pressure build up ahead of it. Okay. Now, one of the problems you have with that is it's not like we have a constant airflow, that's constant running through there, and we could say, hey, this is restricted, because as you're wide open throttle, you're obviously going to have more throttle, more air coming through, or if you're just putting around slowly, you're going to have less air going through. So we can't know what that number, what is the proper number for that exhaust, how much pressure that is actually. So what they do with that is they take that pressure reading and they calculate that into a big old algorithm, and with everything else of knowing what the mass airflow is doing, how much air is coming in the engine, what the RPM of the engine is, and what the load is. And they put all that together. And when all that works together, then they can say, okay, we know this thing's plugged or not plugged. Okay. So most of our Fords are dealt with that way, with just one sensor and how much airflow is coming in the engine. And then we make a decision of whether we're going to regen it or not. Now, some of our heavier trucks and some of our early transits used a delta sensor. In other words, it's going to have a sensor behind it and before it. It could be two sensors, or it could be one sensor with two tubes. And what that's going to do is it's going to measure the pressure before and afterwards, because the one afterwards should actually be atmospheric pressure. So we're going to measure the pressure before and after that DPF and determine its load. That's probably the easiest, most accurate way to know what the load is across that DPF. But so we're going to use one of those two methods, and they're both really accurate. We don't have a ton of problems with them. And so that's how they're going to know when it's time to do a regen on this thing. So then we got exhaust temperature sensors. These are, have you been to any other automotive classes besides mine?
No.
Okay. Our temperature sensors that are like oil temperature, coolant temperature, all those are what we would call a negative coefficient type. In other words, they're as they heat up, the resistance is going to go down. Okay, they're all thermistors, but those are negative coefficient type. These exhaust temperature sensors are a positive coefficient type. In other words, as the sensor temperature increases, so does the resistance. Okay, and it's a positive. That's what it means, be positive. And all that means is just a fancy way of saying, hey, there's a wire that runs through the center of this thing that's wrapped around a ceramic tube, and it just, as that wire heats up, it becomes more resistive. And all we're doing is sending a voltage down in there, and it goes through that resistor and back to the PCM. So we can know, based on the voltage coming back at the PCM, what is the temperature of that exhaust. It's pretty simple. Okay. But you just need to know that these are a positive coefficient type resistor, or what they're going to call a resistive temperature detector. Okay. An RTD. We're going to use at least 3 of them in the exhaust. There will always be one before everything. So we're getting that. Remember, in those 4 temperatures we had coming out of that engine, we had one that's raw temperature from the exhaust. What is it coming out? We're always going to have one right after the DOC, so that we can know that the DOC is working. The computer has strategies that says, hey, I'm dosing this thing and it ain't heating up. I'm going to set a code. I can know that thing isn't working. Then we're going to put one after the SCR. I'm sorry, one after the DOC. I'm sorry, the DPF, the D, whatever. So we're going to have one before the DOC, after the DOC, and then after the DPF. And then we're going to have one at the very end. The one we're going to have at the very end, they're all going to have one at the very end. And the reason we're going to have one at the very end is because if the truck had some sort of failure and was putting raw fuel in the exhaust or oil in the exhaust, and then this thing goes into a regen or something like that, we can create huge amounts of heat in the exhaust and actually turn into flames and blow flames out the tailpipe. Okay. If it gets to a temperature where it's like, this is, we're above a certain number, it just shuts the engine off and you're screwed. It just turns you off. I've never seen one do that. I've always seen the sensors go bad and it thinks it's on fire and it turns the engine off. But I've never ever seen one on fire. But that's its point there. So this is an exhaust in a 6.4. This is the first sensor. Your DOC is right here. And then you're going to have your second sensor right behind it. And then it's a really big DPF in that thing. And then there you have your sensor behind it. And all they're doing is monitoring the temperatures of these things. Okay. These are exhausts in a 6.7. And these are a really good picture. I think I even have a better picture here. Let's do here. This right now, you have your temperature before and after the DOC. And then these are cabin chassis. They're like trucks, heavy trucks, not pickup trucks. You're going to have on this one here, you're going to have the DPF right here. So you're going to have a temperature sensor after DPF. And then you're going to have one in the back. Now, all this numbers here about the model years and all that in the early days, for whatever reason, they had them 11, 12, 14, and 13 in the big trucks. And it just created such a confusion. It's because 14 was actually supposed to be measuring the exhaust at the end, and they switched the exhaust configurations up in these trucks. And I'll explain that here in a second, but it's not important to you at this point. But we just have just to know that this is the placement of the exhaust sensors in these. Now here's a picture of those insides of those two vehicles. So in the, they're flipped, but this one here is a regular pickup. We actually had the DOC first, and then we had the SCR, which we'll talk about on Tuesday, which is for getting rid of NOx. And the DPF was all the way here at the end, as opposed to the cabin chassis versions. It has the DOC here, then the DPF, and then we dealt with the NOx. So what in the world was that all about? Well, what the purpose was in the pickups was if we can put the DPF at the end, they were taking advantage of not only the heat out of the DOC, but the heat generated when we dealt with NOx in the SCR. We used the heat benefit of both of those to keep the DPF clean. And what it did was they actually saw about a 2% increase in fuel economy doing this. Or I think they describe it as 2% less fuel usage. Okay. So you got better fuel economy doing it this way because we didn't have to dose it as much. Remember, every time we're putting fuel in the exhaust to dose this thing, that's just eating fuel. That's just fuel literally peed down the exhaust pipe. Okay. So the less we have to do that, the better fuel economy we're going to get. But you couldn't do that in the heavy trucks because the way they loaded so much, we needed the heat right after the DOC to make that happen. So just a little bit of trivia for you. And another picture of the exhaust on this thing. This is, we'll talk about that next week, but this is just an injector that's actually going to spray that exhaust fluid into the exhaust, into the SCR there. The last thing we're going to talk about today is particulate matter sensors. In 2016, legislation was passed that we needed to know exactly what was going out the tailpipe of these things. And so we have what we have is a particulate matter sensors. And all it is a sensor here that's controlled by a module, and it's a grid or a grid for lack of a better term, or a set of wires or hairs inside there. And what they do is they're completely open circuits to each other. But as if the exhaust has soot coming through because it's got a leaky exhaust or something like that, and it's got, we're getting exhaust soot through the exhaust out the tailpipe, it collects on those grids inside this thing. And remember, those grids or that soot is organic material. And so it actually it's actually conductive. So it would get on that grid and it would conduct electricity. And based on how much electricity is conducted through there, they would know how much soot is actually coming out of the exhaust. Okay. And then it will turn a check engine light on and say, hey, we got a problem. Now, if we just left that sitting in there and you have, remember these things are only 99% efficient. So you have 1% of the soot coming out of there, still making it out the tailpipe. Well, if this thing's sitting here collecting soot all the time, eventually it's going to get enough to be to short out and turn the light on, right? Well, so what we're going to do is periodically this module is going to turn on a heater inside this thing. It's actually going to burn the grid off and make sure that grid is clean so that it's getting a true sample of what's coming out that tailpipe, not a buildup of stuff coming out of it. Does that make sense?
Yeah.
Yeah. So real big. And I know that the Europeans do it a little differently. They actually have a different technology that actually counts the particles coming through. Ours does not do that. This is in America. This is how we do it. I know I've only talked about how Ford does all their stuff. There are some other technologies that are out there, and one of them, and I would assume we'll eventually see them on a Ford product, but one of them is, instead of doing a hydrocarbon dosing, because maybe they can't do it, or they can't do it for fuel economy reasons or whatever, but they actually have electric grids in head of the DOC where they'll actually use an electric heater to heat the air to burn off the DPF. I guess one could argue that all the energy that it takes to heat up, the electricity, is obviously going to be some sort of a load on some sort of a generator that's going to make that happen. So I don't know, the trade-off fuel economy wise or whatever, or maybe it's a space thing or whatever, but there are technologies out there that use electric heaters to do that. There's also other technologies that are out there. We'll talk about the SCR next week and how we're going to use urea and ammonia to strip the exhaust of NOx. However, there's other technologies that are out there that they're using NOx absorbing catalysts and there's other things that are out there. I didn't include them in this course. I didn't include them in your readings. If you had the book, which I think you have your brother's thing, if you're really excited about reading about that stuff, you can go ahead. However, I am not doing anything with that. And I think that's the end of my slideshow. And you now know everything there is to know, or more than you need to know, about all that diesel exhaust so far up to the SCR. Okay. The SCR was a selective catalyst reduction. We say selective, it's because it's only there to treat one thing, and it's selective in what it does. And it's very specific. We're going to talk about how that SCR works. We'll talk about all the chemistry of it, and then we'll also talk about how the DPF or the DEF, which is the diesel exhaust fluid, how that interacts in that, and kind of get them all together. And at that point, we'll have talked completely about what's going on inside that after treatment system. I'll let you play with you have your web-based courses to deal with in that this week. On Monday evening or Sunday evening, the course, the next week's will open up. It will help you if you just take the time Sunday night or Monday to there's an 8-minute video I think in the first or second module, or module inside that module. There's an 8-minute video about that SCR and what's happening chemically. It will really help you if you watch that first, and then you can call me out if I get it wrong, because but it's a really good video. So watch that before you come to class on Tuesday. We'll do that. Tuesday should be a full night. But then after that, we'll get together on the following Tuesday. We'll just talk about OBD2 systems and stuff like that, and then you'll be done. Okay. Do you have any questions? Does it all make sense?
Yeah. So the last day is the 3rd?
The last day is the 3rd. That would be right. It would be, because the 30th is a month. Wait a minute. Yeah, 30th is a Monday. So the 1st, we'll talk about OBD2 systems and some of the computer stuff. And then that Thursday, which would be the 3rd, we would be done. So, and you don't have to come to that. And we'll see if these other guys come. The heck.
Cool.
All right, dear. Have a good night.
You too. Thank you.
And I'll see you next Tuesday.
Okay. Happy Thanksgiving.
Hey. I'm working Saturday, and I don't know I'm not sure what the workload is looking like, but if I get something I look like I'll have on Saturday a diesel that we can do something with, are you interested in that kind of thing on Saturday afternoon?
Yeah.
I can't make any promises because I don't know what my workload will look like, but
That's
I
fine.
I should be able, I might know by tomorrow.
I get off work at 2.
On Saturday?
Yeah.
On Saturday? Are you up there in Escondido or down here?
Kearney Mesa.
Okay. Let me look and see if you know, if I can, if I got something I can put together the quality that afternoon, if I can, and we'll see
Yeah, cool.
if
I
there
definitely
is,
go.
we'll see. No promises.
Because I've been waiting.
I know.
I was telling Nacho that I was like, Kevin hasn't like hosted anything yet.
I know that. I haven't. Yeah. Well, we'll see.
Okay.
I will find some. I'll have to see if I can find something that will be exciting that we can do. You know,
Okay.
something. You want it to be.
Doesn't have to be exciting. Just like learning, anything learning. I really enjoy it.
Okay. I'll find. Well, you know, I know I have a used car. It's an old 6-liter though, but we might be able to figure something out. Okay. All right.
Thank you.
See you. Bye.